Hello everyone, greetings of the day. Today we are going to start with the module 5 of Control Systems Engineering of 6th semester Biomedical Engineering students. And 5th module is all about state space analysis of control systems. State space analysis. In modules 1 to module 4, what we were seeing is the various types of system analysis called the classical system analysis. In classical system analysis, we were depending upon the linear differential equations and the transfer function models, and then subjecting the system with this various inputs in time domain, analyzing the system's response in time domain, giving various frequencies to the system and seeing what all are the various outputs when frequency is changed in the input. So that type of analysis is called classical system analysis. And now we are going to see an entirely different system analysis method that is called the state space system analysis. So there are certain disadvantages for our transfer function method or transfer function model of approach. Let us see what all are the disadvantages of that classical system analysis, which is based on the transfer function approach. So first of all, we know the transfer function is defined as T of s is equal to if y of s is the output of the system and if x of s is the input of the system. Transfer function is defined as ys by xs with the initial conditions all 0. So if x of t is the input, its Laplace transform will be x of s, and if y of t is the output, y of s will be the Laplace transform of y of t. Now the ratio of output by input with all initial conditions subjected to 0 is called the transfer function model of a system. Now from the definition itself, it's very clear that we are assuming that the initial conditions of the system is 0. But there are systems which has got a definite, maybe if it is a mechanical system, there can be certain there can be some velocity, or the system can have some initial position. All those things we are assuming to be 0 and then analyzing the system with the time and frequency domain approaches. So these initial conditions, that assumption itself is a drawback of the transfer function approach. So if the initial conditions are not if there are some initial conditions, we are not taking care of that. So the second disadvantage is, so this is the first disadvantage, the initial conditions are all assumed to be 0. Now the second disadvantage is, most of the systems we dealt with single input and single output. We have x of t as one input and we have y of t as the corresponding output. We are not dealing with the x1, x2, x3, different inputs we are not subjecting the system, and we are not checking what all are the outputs for those inputs. So usually transfer function method or the classical method deals with the single input, single output systems. So if there are multiple inputs, there can be multiple inputs for a system and there can be multiple outputs of interest. But if you are only dealing with the single inputs, single outputs, then again the transfer function approach only deals with the single inputs and single outputs. If there are multiple inputs and multiple outputs, we are not able to actually take care of the system. So that is the second advantage. Third disadvantage is, when we talk about the classical system analysis, we are only dealing with the linear time invariant systems only. The system should be linear and the system should not vary in time. The system parameters should not vary in time. So transfer function approach deals with the linear and time invariant systems. If the system becomes non-linear or if the system parameters changes with respect to time, we don't know what to do. So these are the major disadvantages of the classical system analysis. So the disadvantages are listed here. So in order to compensate for all these kind of disadvantages, we are depending on the state space method of system analysis. In state space method, what we do is, we are not assuming the initial conditions are 0. If there are initial conditions, we can accommodate them into the system model, and multiple inputs you can take care of, multiple outputs you can take care of. And if the system is non-linear, obviously you can take care of that systems in a state space model. And if the system is time variant or invariant, that also you can represent using state space methods. So in a classical method, we have a system with some system. Usually the inputs will be linear inputs with x of s as the input and or x of t in time domain, and y of t the output, y of s in the time domain the output. So this is a general representation of a system in the classical analysis. Now when it comes to the state space analysis, we can represent a more generalized representation. You can have multiple inputs, x1 of t, x2 of t, up to you can have xn of t, or let it be xm of t. So many inputs you can have. Hello everyone, have a good day. We are going to start with the module 5 of control systems, that is state space analysis of control systems. So far we were seeing about linear time invariant system dynamics with the help of transfer function. Hello everyone, greetings of the day. Today we are going to start with the module 5 of control systems. Module 5 deals with the state space analysis of linear control systems. So far we were seeing about various types of system analysis like time domain analysis, frequency domain. Now again in the classical system analysis, you can have some coupled systems with lots of, if it is a mechanical one, there can be frictional elements between various nodes M1, M2, let this be spring constant K1, the frictional element B1, there can be one more friction element, another spring coefficient, another node, likewise all these things, it is there, you are applying a force, and you may be interested in knowing the position of one of these mass x of t, like that. Now when you represent the transfer function of the system as f of s divided by, x of s divided by f of s, this will be the output by input transfer function, you will get something in some ratio of two polynomials in terms of s, you will get, and that is not telling you exactly what happens inside each of these elements. If you are interested in knowing what is the position of the spring, or what is the velocity, or what is the rate at which this frictional element is moving, or if you are interested in knowing what is the position or the velocity of this intermediate element, that is not, you will not be able to obtain that in the transfer function case. So that is also accounted in a state space analysis. You will get a lot of intermediate system variables you can consider, and all of those values, whatever is interested to you, let it be. And one more thing I wanted to tell you, in classical system analysis, the notation used for input is x of t and output y of t. When it comes to the state space analysis, most textbooks follow a different type of notation, and u is the input, u of t is the input, u1 of t, u2 of t, etc. up to u m of t, like there are m inputs, y of t is the output, obviously output y is, and if you wanted to know what all are the internal behaviors of the system, if some internal variables, position, velocity, or you can tap all those informations and you can call them as state variables, x1 of t, x2 of t, etc. up to you can have xn of t. So these, in classical domain analysis, we have only one input and only one relationship between single input and single output only you will be getting. In state space analysis, you can subject the system with simultaneously with the multiple inputs, and you will be able to obtain what all are the outputs for each of those cases. And in addition to that, you will be able to get some information regarding the internal details of the system, some internal variables, and in state space domain we call them as state variables. State variables. So these are the outputs, these are the inputs, and in addition to that you will get an information about the state variables also. Now what is a state variable? State variable means the minimum set of variables with which you will be able to predict the behavior of the system for a time greater than t0, t0 is initial time, if you are able to know the initial values of those variables along with what all are the inputs applied to the system. So the minimum set of variables along with the inputs and their initial values, if you are able to know, you will be able to predict the behavior of the system in future. So those minimum set of variables are called state variables. Now transfer function approach, we have a general formula. Transfer function is output by input with initial conditions 0. And in state space analysis also you can have a generalized representation. So it's like x dash of t is equal to a into x of t plus b into u of t, and y of t is equal to c into x of t plus d into u of t. So in transfer function approach, you have a single equation, output by input equation, but in state space equation, you will have a combination of two equations, and this first equation is called state equation, and the second equation is called output equation. So every system, if we are representing it in the state space model, you have a state equation and you will have an output equation. And these two equations together are known as the state model of the system. It's called the state model of the system. Now here, x of t is the state variable, and u of t is the input variable, and y of t is the output variable. So u of t is a number of inputs can be there, y of t again a number of outputs can be there, and state variables, you can have a number of state variables. So if I am representing like this equation like this will obviously come in the form of a matrix. So I can now write a generalized state space equation. x1 dash of t, x2 dash of t, etc. up to xn dash of t, a column vector equal to a matrix A with certain values and another column matrix x1 of t, x2 of t, etc. up to xn of t. Now you have, assuming there are n state variables, this will be a 1 by n matrix, and again this is a 1 by n matrix. So your matrix A should be of the order n by n. Here x1 of t, x2 of t up to xn of t are the state variables. State variables, and these are the first order differentials of state variables. So the first order differentials of the state variable equal to a matrix A multiplied by the state variables in its original form plus the matrix B multiplied by our input let u1 of t, u2 of t, etc. up to let there are m inputs, um of t. If this is a 1 by m matrix, then obviously your matrix B should be an n by m matrix. So this matrix A can be A11, etc., A21, etc., finally ANN. Again B11, etc., B12, etc., finally BNM. So this is the state equation. Now you can write the same thing for y of t, the output equation. Output equation y1 of t, etc. up to let there are p outputs, yp of t. So this will be a 1 by p matrix. Output is equal to the matrix C into our x1 of t, x2 of t, etc. up to xn of t, the state matrix 1 by n. So if it is p, then a p by n. This matrix C should be a p by n matrix plus the matrix D into the matrix U, u1 of t, etc. up to um of t. If this is a 1 by m matrix, then this should be a p by m. So this makes the complete general form of the state equation of a system. Now having understood how the state space representation of a system can be done, now we are going to see a mechanical system, how a mechanical system can be represented in the state space model. So this is our general format. Now consider a normal mechanical system that we have studied in our first module. A frictional element B and its coefficient of velocity is Tk and a single mass, and you are applying a force F of T. You are pulling the mass and you want to see what will be the position of the mass after a certain time, x of t. So our transfer function approach, the system will be transfer function T of s is equal to x of s divided by f of s. Now when it comes to the state space analysis, for a mechanical system, the minimum set of variables whose initial values along with the knowledge of the input, you should be able to predict the output. That is what our intention is. In state space analysis, the minimum set of state variables we need to first of all find out. So for a mechanical system, as I have already told, the position and velocity are the variables of interest. Now anyway, first let me write the linear differential equation governing the system. We have f of t is equal to, after writing the force balancing equation, you will get f of t is equal to m into x double dash of t plus b into x dash of t plus k into x of t. X of t is the position, x dash of t is the velocity, and x double dash of t is the acceleration. So this is a force balancing equation. Now I want my variable of interest is position and velocity. So x of t is my position, that is my I am considering that as one of my state variable. So let my x of t, I am considering my first state variable x1 of t. Let x1 of t is equal to my output position, that is the first state variable. And I am considering another state variable x2 of t, let that be the velocity, and velocity we know it is x dash of t. X dash of t. So the position and velocity I am considering as the two state variables. Now this equation I can rearrange. This equation as x double dash of t is equal to f of t m into x double dash of t is equal to f of t minus b x dash of t minus k x of t, or x double dash of t is equal to 1 by f by m, f of t by m minus b by m x dash of t minus k by m x of t. And already I have assumed my state variables as x1 of t is equal to x of t, that is a position, and second state variable x2 of t is equal to x dash of t, and it was the velocity. So having identified the two state variables, now I should write two equations, state equation and output equation. So let me first write the state equation. In my state equation, I should have the first order differentials of the state variables x1 dash and x2 dash. x1 dash and x2 dash. Now I have x1 dash is equal to x2, and let my matrix A be blank there. First of all, I am going to identify what it is. So it should be x1 of t and x2 of t here, the original form of state variables. The left side should be first order differentials of state variables. So x1 dash of t is equal to x1 dash of t. Again, x dash of t is x of t is x1 of t, then x1 dash of t is nothing but x1 dash of t. So what is x1 dash of t? x1 dash of t is x2. So this should be 0 and this should be 1. So that 0 into x1 of t plus 1 into x2 of t, that is x2 of t. So x1 dash of t is equal to x2 of t. So this equation is done. Then I should have a value for x2 dash of t. Now x2 dash of t is x dash of t. Sorry, x2 of t is equal to x1 dash of t. So my x2 double dash x2 dash of t will be what? x2 dash of t is equal to x double dash of t. x2 dash is equal to x double dash of t. So we have an x double dash of t here. This is what? So I am substituting this x2 dash here. I can rewrite x2 dash of t is equal to f of t by m minus b by m into x dash of t. And what was x dash of t? X dash of t was x2 of t. x2 of t minus k by m into x of t was our x1 of t. So I got the second equation x2 dash of t. I wanted x2 dash of t. x2 dash of t is what? It is ft by m, where ft is the input. So input should come as part of the matrix b into ut. So I am going to leave it this right now. B minus b by m into x2 of t and minus k by m into x1 of t. So the term corresponding, the coefficient of x1 is minus k by m, and the coefficient for x2 is minus b by m. So this part is done. This and this we have accounted. Now it should come as part of the matrix B. So it is, and again in this along with f of t, we have only one input, that is f of t. So it's a 1 by 1 matrix f of t, and this is coming for x2 dash of t. So for first x1 dash of t there is nothing, and for x2 dash of t, for the equation for x2 dash of t we are seeing this thing. So it is 1 by m. Now you will just see whether this equation is getting balanced. What is x1 dash of t? x1 dash of t is equal to 0 into x1 plus 1 into x2. So it is x1 dash of t is equal to x2 dash plus 0. So our equation is only x1 dash, previously it was written there, x1 dash is equal to x2 and x2 dash is equal to x1 of t into minus k by m, x1 of t into minus k by m, then minus b by m into x2 plus this time 1 by m into f of t. So this completes our state equation. So one part is done. So this is the state equation, and it is in this form: x dash of t is equal to the first order differentials of state variable is equal to the matrix A into the original form of state variables plus the matrix B into the input matrix. Now the second equation is y of t is equal to cxt plus dut. Now in our mechanical system we identified y of t is nothing but the position x of t. And what was x of t? X of t was, I can write it as output variable y of t is equal to matrix C into x1 of t, 0 and x2 of t, 1, 0 plus matrix C along with the output. We don't have any, we are just talking about the position alone. Their input is not a relevant thing, so it is 0. So this completes our state space model of the system. This is our output equation. So this is how in state space domain, how do we model a system? There will be two equations, a state equation which will relate the input and the first order differentials of state variables and the state variables itself, and another set of equation where the inputs, the state variables and the outputs are related. In transfer function approach we were only talking about the input and output, and we were completely omitting the internal state variables as such. But in state variable representation you are able to identify a set of state variables whose initial values along with the information about the input for a time t greater than t0 will be able to predict the behavior of the system in future. So it's a more generalized representation. It's more advantageous whether the internal state variables changes in time or whether the system is linear. All those things are getting accounted in a state space representation. Now the state space representation is not a unique one. Depending upon the choice of the state variables, depending upon your variables of interest or the way in which your equation is written, there are different types of state variable representations. And I can give you a comprehensive look at what all are the state space, different forms of state space representations. The first form is known as phase variable form. Phase variable state variable form. Then there are two canonical forms, and they are observable canonical form OCF and controllable canonical form CCF. And there are similarity transformation approaches also, similarity transforms. So there are three ways in which you can represent a system. One is a phase variable form, or it can be a canonical form, or it can be a similarity transformation form. So in our syllabus, only these two things are to be studied. So in the next class, I will show you how to represent a system in these type of forms. Okay, that's all for today.